We're QuantrolOx. What we aim to do is to ultimately automate quantum computers. We imagine them in some near future to still sit in a crash dot surrounded by a data center, and we basically want to make sure that it runs smoothly. So who are we? We are a small company that was spun out of University of Oxford. We're now based 19 people in Finland and in UK, and we are distributed and working together on our software. So today we will show you the first official version of our product. We launched it 2 days ago for this conference. And here with me are Freddie, who's a product manager, Dominic, co-founder and head of quantum technologies, Tommy, senior machine learning engineer, and then in Delft you will see Chachu is there, and of course our CEO and Andrew Briggs, co-founder, is also here. So why do we do this? So today, at best, we talk about superconducting chips, and we know that if you're lucky, you can play with chips of this size. But the problem is that it's notoriously difficult, as we heard throughout the conference. No matter how big you are, it's not an easy task to automate, calibrate, and make qubits ready for algorithms. And the algorithms are quite complex, and if we want to have accurate calculations, we need more than 1 million physical qubits to be in constant state of tune. So that's why what we were set out to do is develop our software in the Lucian refrigerator with control electronics of, at the moment, QBlocks and QM. We have Zurich Instruments in the pipe. With QBlocks, we have established a very close relationship, and we want to advance this development further and have it sooner to our customers and you guys in the lab. And the chips that we use are those from Quantware. These will be so-called Sopranos. They're 5 qubit transpons, and with that as well, we have special partnerships, so we make things much quicker and smoother. And I'll hand it over to Freddie, product manager, to tell you more about the product.
So I'll now give a brief introduction to Quantum Edge, our product. So first of all, what is Quantum Edge? So Quantum Edge is a software that automates the tuning and optimization of superconducting quantum computers. And in this demo, we'll show how the software integrates with multiple hardware types, and through that integration is then able to tune single qubit gates for superconducting quantum computers. And in that demo, we'll run 3 times, once with QBlocks control hardware, once with a simulator, and once with quantum machines. And and then that's being run remotely from the Blue Force lab in Delft, with the Blue Force LD containing a Quantware Soprano chip with 5 qubits, and we'll run those electronics on that chip. So the actual product can be broken down into 3 key functions. The first being QPU monitoring, which is mapping the key metrics onto the qubits on the QPU. Then automation workflows, which tracks the progress of that automation, and the data visualization, which allows you to deep dive into the results. That's then all brought together to integrate with the leading control platforms. So I'll now run through the 3 key screens. So the QPU monitoring screen, allowing you to map key metrics such as characteristic frequencies, T1 and T2, onto qubits on the QPU. But this is obviously just on a 5 qubit processor, and with the evolution of the quantum industry, we expect that number to grow significantly. So obviously the design team is thinking through how that will grow. So here's a 21 qubit system, and also kind of 100 qubits for the future. Then the automation workflow screens allow us to track progress of the automation and get regular status updates of the workflow. And then the data visualization screens allows you to analyze and go into more depth into the results from the experiments. And then finally, just to kind of set expectations of what Quantum Edge can do right now. So we can automate the tuning of superconducting transmon qubits with pre-selected control segments. We're currently integrated with QuantrolOx and quantum machines electronics, with more on the way. And finally, the data visualizations are interactive on that screen. I will now pass over to Dominic, who will go through in a bit more depth the demo.
Thank you, Freddie. Lovely to see so many familiar faces today, but also people new faces. If you're interested in learning more, please feel free to come down and visit us at the booth. But we'll go through this in initial detail just so you can understand what the setup is that we're using and what the actual experiment looks like, so we can have some better back and forth discussion. So, live demo, I'll start from the sample. We're using a spine, as we mentioned a few times, from firmware. Rough architecture looks something like this. And then you see sort of data representation of the same visualization of the same thing. So you can see the structure is kind of, we've got a high, mid, low frequency for high qubit architecture with a probe line that travels around the device and couples to all resonators. This is placed in the LD dilution refrigerator in Delft. You can see actually there's two samples in here. This is we're using demonstrating on both of them, and one is connected to quantum machines, and one is connected to QuantrolOx. We'll mostly be talking about the QuantrolOx one for this demo. For just cases of having a chat about also how the fridge is set up, you can see we've got some, the way it's set up is drive line, flux lines with some light attenuation, some filtering, and then readout lines with isolator and amplification stage. We don't have anything like a tuple in this system, but this is really more of a development fridge for our experiments and getting software development working for us. Then this is all feeding into a device sitting in a magnetic shield, which I pointed out here earlier. In terms of the control electronics on the QuantrolOx side, which we spend most of the time talking about, we have 4 product cards in the mix. So for our drive line and for one of our qubits, this qubit 4 here on the top right, we our readout line, we have our input going here and our output coming out here. For our drive, we have our drive coming in like this, and we use the output of the drive QCM RF card. And then for flux control, which we aren't really going to be showing in this because that's more part of the initial tune-up, or when you're doing 2 qubit gates, then we have a S4G for flux bias, and we have a QCM for flux pulsing. And maybe finally, just to talk about how the software is set up, we have quite a lot of flexibility on how we can distribute the software. We made it composable, so back-end, front-end, and all these things can be placed in different places. The way we're running it today, just for speed and to reduce latency, is we have the back-end and the whole application running in Delft actually on a little server sitting right next to the instrument rack, and then we're talking right directly to the QuantrolOx cluster. And then here today, we're just accessing a web page remotely, essentially over some sort of cloud network. Finally, on this point, it might be nice to show the lab, so actually we also have an engineer here, so actually if you want to have a look. This is live stream of the lab.
Yep.
And
Chachu
is also there, manning the system, making sure it doesn't blow up during the demo. But actually things have been running okay. Maybe Chachu, you can gesture towards the cluster and maybe gesture. Yes, there you go. And you can see also the SPI rack, and sitting on top here, actually, you see an OPX. Yeah. Oh. Yeah. Okay, cool. Then final point, more slight expectation setting, just to reiterate. The scope of the demo really is just to show mostly the software architecture and how it can be used for multiple different things, and how we've thought about a lot of scale and how we've thought about how you can compose these experiments. We're really only showing basic automatic single qubit calibration. Things that we aren't obviously including is that are important, things like more coarse tune-up that comes before this 2-qubit calibration, advanced single qubit calibration. Perhaps you might want to do more advanced things than just this, and then customizing details, so adding and changing things. But without further ado, Tommy, take it away.
Okay, so as Freddy already showed you the quick intro to the different screens, so here's the QPU monitoring screen, which gives you an overview of your chip. So here we have the 5-qubit soprano. You can see the qubits and the couplings here. And after you have run the calibration, then from this drop-down list you can see different metrics superimposed on top of the qubit layout. So frequencies, fidelities, and different characteristic times. So you can see them in a nice overview manner here. But since we haven't run this yet, the database is empty and we have nothing to show here at the moment. And also here on the left-hand side, you see the tuning progress indicators. And as Dominic mentioned, the flux biases have been tuned already manually, so that's your green, but soon we will show the single qubit tuning. And on the drop-down list, you can see the three systems that have been configured. So we have the QBlocks instruments and quantum machines and the software simulator. And now we will start with the QBlocks, so we will select that. And now you can see that 4 of these qubits have been crossed out, so only this 1 qubit has been prepared for the simulator, but we are not calibrating these other 4 qubits at all here. Then, well, we have the data visualization page, but since we haven't run anything yet, this is empty. So the most interesting thing here is now the automation workflow page. So this shows the progress of the calibration in more detail, and so let's not go through these different boxes to see what's in there before we start running the actual workflow. So most of these boxes are what we call control segments. So control segment is a combination of an experiment and the analysis of the measurement output from that experiment. So for example, resonator spectroscopy. It performs the resonator drive frequency sweep as the experimental part, and then the analysis part extracts the resonance frequency from the measured data. And once we have that, the information is passed on to all of the following control segments, so they have access to that information. So then the next box here is qubit spectroscopy. So similarly, this performs a sweep of the qubit drive frequency, and then the analysis part identifies the qubit transition frequency from the measured data. So now we have the resonator and qubit frequencies, then we move on to the power Rabi. So that performs a Rabi experiment with an amplitude sweep. And then the analysis part identifies the amplitude for the pi pulse. So now we have the basic components, the frequencies and the pi pulse amplitude. Then the next box is Ramsey. So this performs the Ramsey sweep, and in fact it performs a 2-frequency Ramsey. So basically 2 Ramsey at 2 different frequencies, and that enables us to, first of all, extract the T2 star dephasing time, as well as it gives us a more precise estimate for the qubit frequency. And then the next box, that's a bit different. So that's not a control segment, it's essentially a decision element. So if the preceding Ramsey control segment, if it changes the qubit frequency by more than a threshold, which currently is 1 megahertz, then what happens is that we loop back to the Rabi. So we take a new Rabi with a corrected frequency. And well, actually we also do a new Ramsey, which might not be strictly necessary, but in order to keep things simple, we also then run the Ramsey again. And then when the qubit frequency is no longer changing, then we move forward to the next control segment, which is now single shot readout. So what that does is it prepares the qubit in either the ground state or the excited state and measures that. And then the analysis identifies the IQ voltages for the ground state and excited state. So it gives us a classifier which can be used to classify the measurements to 0 or 1. And also it gives us an estimate of the T1 relaxation time. Then we have the all XY control segment. So that performs the all XY experiment, which in our case it contains 21 different elementary experiments, different combinations of the X and Y rotations. And as most of you probably know, it can be used to diagnose then different kinds of errors in the calibration. Currently, we only show the output as a graph. In the future, we would hope to have some kind of automatic analysis to identify and diagnose the possible errors for you. But at the moment, we only show the graph of the measurements. And then we have the single qubit randomized benchmarking, which gives us the single qubit gate fidelity. And the final box, that's again not a control segment, but it just stores all the extracted parameters in the database. And I think now we are ready to start the actual demo. At this point, do we have any questions? If not, then we can. Okay, let's put up the video stream there so that we can see what we are doing here. Keep it on top. Okay. I guess we can now. So now we have selected, on the left hand side we have selected Q blocks, so we first run the demo on the Q blocks. And start. So now I'll hand to Dom.
Thank you, Tommy. Yeah, so quite a comprehensive overview of what we're trying to do here. I mean, I guess this is quite a clear sort of single qubit calibration sequence, but it is still, I mean, a lot of work to implement for including instrument integration and all the analysis tools and getting it right. So it's a kind of an example of how we can quickly and quite rapidly get to be able to do these experiments very quickly using this framework. We've already put a bit of focus on how fast this is going. We've been putting a lot of effort into making sure that we've done the software engineering quite right so that everything flows quite quickly. So we've already managed to make it to Ramsey. And to give you a benchmark time, because unfortunately we're covering up the notifications here where the times are shown, the whole thing will run about 1 minute and 45 seconds. So that's not bad. And we're not making use of too many crazy techniques here. So it's not that's already quite nice. And a lot of the speedups have just been and just stupid practical things like implementing things and trying to reduce the amount of interfaces and logic between different parts. I mean, we're already at single qubit randomized benchmarking, and that is actually the majority of the time for this sequence, so it's about 40 seconds. Whilst we do that, I can just quickly talk about how the actual control segments are configured. So you have the ability to be, and these things are described. So this isn't really a static thing. I mean, at the moment we'd be showing a static graph, but this is not something that is fixed and can be altered. And the topology and the mapping between these things, we have the freedom to be able to alter. It's not currently a feature yet for the user to be able to alter it. This is again something we're working on. Now that we've finished, we can quickly go to the data visualization page and actually show the data that we measured and how things were treated. So now, before there was nothing there, now we see all the data. And what's nice and handy about the way we've implemented this is you have this nice little window here that you can use to manage all the information that is being generated, and then you can see the plot over here on the right, and you can actually, it's a plotly style graph, so it lets you interact with it, and you're able to even turn on and off interesting features about the data visualization. So you can remove the analysis if you have to take, I don't know, some data to a group meeting or something like that. So in the first experiment, as Tommy said, we're just doing a frequency sweep and on instrument, and then we're taking the data up, and then we're finding a resonance. That resonance is then stored in some sort of shared context between all the experiments, and that is pushed forward so that the qubit spectroscopy can run with that value and do the same thing. So they're inside that box. Again, we're doing a frequency sweep, and we're just trying to find identify another resonance, and see the analysis again plonked on top of there for your visualization. And actually, this time now, we're measuring IQ in modulated voltage, so we're actually projecting information. So we have a secondary axis, but you see in the secondary axis there's no information, as we would hope, but it's there in case you need to look at it, and in case you want to try and debug with the analysis is failing, which is one of those things that's annoying and can happen in some cases. With this information, we can move on to the power Rabi, and you can see the kind of expected Rabi oscillations, and the pi pulse that we extract for this. And again, projection, toggleable, and information there for you. We're using this information, and Ramsey is available to us, and we can run the Ramsey experiment. And you see the two different frequencies that we perform the Ramsey experiment at, and you see some sort of detuning. Actually the detuning value here, and the information that we extract, and you see actually also what the analysis thought about the data as well. Finally, onto the single shot readout. From this, we actually have two versions of the plot, just showing here at the moment. Just one with the IQ plane data and the discriminated model that you would generate from that, and then one with the projected plane with the generated model and the discriminated line there for you, so you can have a look and see where that was drawn and why. Using that, using all the prior information, we move on to all XY. And you see producing a reasonable XY, maybe a little bit of miscalibration with a few things, but actually it's pretty close and accurate. And then finally, single qubit randomized benchmarking. You can see the number of different gates that we perform here, that goes about 700. You see also the exponential clip that we generate. And the way this experiment is really working is as we expect this thing to decay from one state to the other as we apply more and more clifford gates, because the errors compound, and then the rate of this gives us information about what the fidelity is. So this information, it's nice to have this, and you can have a look at this for debugging, but if you jump onto the QP monitoring screen, the same information is generated there and placed there, so you don't have to go deep diving for it and find the exact plot. So the frequency that we just extracted on that plot, sitting there, and you can have a look at the value. Other example, maybe gate fidelity. We're able to go and have a look at that and then see if we're getting a clifford gate fidelity of 99.5, which is that's decent. Then we can have a look at other quality metrics as well, extracted by some of the other control segments. T1 here, we are probably getting about 11 microseconds, so nothing spectacular, but it's decent enough, and it's useful enough for this demonstration for our development. Finally, I guess, now if you want an example of this running on another system, we can jump over to the simulator, and here we have access to all of the different different qubits, and you can actually see what it's like if we ran this thing on multiple qubits. So if we hit the automation go back to the automation workflow page, we can hit start workflow and we can watch, a typical like a simulated version of what this might look like in sort of a realistic type case, and we use some tricks to make a simulator that feels and acts and behaves like what you'd expect it like to be using a real system behind the back end. It's nothing complicated, but it's made to be fast and made to be useful for development. Some other interesting information about the control, this workflow object here. There is behind each one of these, there's almost like a shared variable scope that we have the ability to control, so we can place values and information into it. And that's where the information is being shared forwards to other control segments. But it doesn't necessarily mean that, for example, you extract a qubit frequency. It doesn't mean that's the only frequency you can ever have inside that scope. You can have other values, and you can use that in comparators, and you can really think of this as almost like a program to that point. And it's part of the design principles here. Other things I'd like to just point out is we have also these error cases and success cases. What you really should think about these things as having is like ports where you can plug them into each other. And for example, in the case that analysis fails and it determines that there's something wrong, it will come out to the other port. And we want to make sure that we keep to that sort of interface so that if there is no resonance there, you should come out the failure port and you should be able to trust that analysis. We can go back to the data visualization page just to see some cases, and now we've filled up our data visualization page quite a lot, so it might be nice to maybe focus on the simulated system on qubit 3, for example. And we can use this nice search feature to be able to find that, and we can see all the qubit 3 run data that we just generated. But we have the ability to obviously filter by other details like control segment type and other things. Finally, you can see all these examples. We can go do all the qubit spectroscopy measurements, simulated qubit spectroscopy measurements, and perhaps look at, say, the single shot readout plot or something like that. Finally, after all this, of course, we're generating more and more data. So this is also then, again, now we've generated 4 or 5 qubits worth of data. It's plonked back onto the QP monitoring screen in a nice easy way for you to be able to look at. So here are all the qubit frequencies, as I was talking about earlier, high, mid, low frequency type arrangement as we'd expect from the soprano, even though it's a simulated system, so of course. Then you can see other information again, and for example, gate fidelity. It's a simulator, so it's not really representative of a real system. Finally, I'd like to end, but first I guess we jump back to the slides and just show what the sort of the QBlox demo is intending to get overnight. So we've been running this. I think I ran it over 100 times last night just to see how it runs and see whether it fails. No failures, so the point is it's rather reliable. If you're interested in coming down to see it running, it'll be running on the booth as well. We have it pretty operational all the time. And if you move on, you can see the kind of values that we were extracting on average. I don't have a time series plot of these values, but we could generate them if you think we're interested. But this is the kind of values that have been going on overnight for the QBlox demo that we just showed, just to make it a more representative sample instead of just this one case. Apart from that, I'd like to thank everyone and maybe back to Yana.
Yeah. Thank you. Thank you, Tommy. And now, if you like to start with questions, that would be great to hear. On to the team. Yes, go ahead.
We're just curious about, so typically when you start an experiment, you're not really aware of the readout settings, and that's also something you need to optimize it. And typically that strongly determines how fast you can do your calibrations. Like if you have a bad device, then you need to average a lot. And so is this robust to things like that? Does it determine from the data if you have good SNR and what do you need to do, and whether you can do something like an active reset or things like that? Does it take those decisions as well?
We're extracting values like SNR and information like that, so we could definitely calculate that. And we would include that as part of the decision-making process for doing a more complicated workflow. Like that is something we do track, and we are actually tracking. We have the ability to track every single variable probabilistically throughout this entire scope. So we have output uncertainties and understand exactly when we should be executing what and under what conditions. We aren't doing that in this case, and the initial tune-up period, where also the part that you allude to, that also is not we're not actually actively doing that.
So one of the requirements here would be then that you have a good readout to start with.
Yeah. So we'd expect to have a pretty decent. We didn't actually show the readout fidelity. It's there. The single shot fidelity is not brilliant, but yeah.
Okay.
Yeah.
Hi, so I had 2 quick questions. So the first is, how easy is it for a user to add something to the workflow? So if I want to define something like, I don't know, F state readout, and then I want to characterize the leakage to the F state during my pulses, is that something I can do, or would I have to ask you to do it and then?
So the answer has 2 facets to it. At the moment, we are making these control segments and guaranteeing their support against different control hardware platforms. And that means, at the moment, it makes it quite hard for users to be able to add anything. And actually, that is something, of course, we've got a lot of interest from people to be able to do that. And we are thinking about that actively. The other point, if it can be achieved by one of the control segments that exists, then it's quite easy to change the settings or the parameters around them. So they're not like fixed entities. It doesn't just do one action. It has, sweep range and all this, settings for like the sensitivity of analysis. So you can change things to other conditions if things are providing you issue. Or imagine, for example, you don't find your resonance and you say, okay, I'm going to kick back to another larger frequency sweep trying to identify something. Yeah, that kind of use case is easier to add. So it's easier to play with the blocks than to add more at the moment for user. But even then, we don't have the editability feature to do that simply. It just sits in a configuration file. This is something also these features for changing things is something we are actively thinking about there.
Sorry, and the second quick thing about the editing the workflow is parallelization an easy thing to do? Like if I just have separate control chips for separate parts of the quantum chip, can I just characterize them separately but parallelly?
You mean if you've got separate control hardware, or if you've got one piece of control electronics and you just want to characterize 2 qubits in parallel?
Well,
or both
I don't know,
conditions.
if I'm using the new OPX 1000 and it has how many ever input and output channels, I should be able to do things parallelly on it if they're addressing different qubits, ideally.
It has the feature to do that, yes,
right.
And we have the capability to just parallelize. These things run in multiple different threads. That's the answer to that. Currently, we're just saying on the simulator, we are just currently only ever executing one in sequence, just for the case of the demo, so it's clear. But on the software side, that's not really a big issue. It becomes a bit more complicated when certain control electronics do and don't support certain types of capabilities. So they might only support this. There's two main ways of doing the parallelization. You either bring everything together and let everything globally sync together, or you just almost have this instrument that is completely divisible and sliceable on any block. The second form is really easy for us.
Thank you. Have a couple questions. Like first of all, I'm interested to see how do you define the search space for a specific QPU? How easy is to change that? If you want to plug a different QPU there, do you have to go to every single of the boxes and change some constants over there, or can I have a configuration file that's agnostic?
So you can have a template for all of these that you don't have to change. So in that case, you don't have to go and change the values every single time. But you would have to go about designing that yourself. right? Or we would have to, at the moment, it would be a matter of us supporting the changes of that.
Okay, and secondly, you mentioned that the variables are probabilistic under the hood, right? So it doesn't mean that you are doing Bayesian inference all the way through the process. You can store the posterior distributions to later reuse them in like a recalibration.
We are not doing that in this case,
so
but we have. I mean, every value could be a probability distribution, no problem, and the analysis can output that, and we can use that to refine estimates. So we can, instead of just trying to include just the ability to execute something and trying to iterate, we can iterate until the variance is low, which gives us a lot more flexibility for actually trying to do things like that. It doesn't, but Bayesian inference itself in the raw form is actually quite slow. So it doesn't mean that we'll be implementing Bayesian inference in all these blocks. A lot of work is going to go into trying to make these things fast and make the analysis fast in specific use cases, whilst keeping the benefits of both blocks. And that's kind of making the analysis good and making it adhere to this port sort of framework, and actually making that work for end users is actually one of the biggest things that we're trying to work on, and making sure that it works well.
Okay, and one last quick one. Since you mentioned that you support different instrument backends, essentially like QBlocks and quantum machines, right? Is there any difference in performance in like single qubit based fidelity and stuff like that between them using the workflow?
Yeah, so we can run the quantum machines one as well, and it's available right now. The reality is this is comprised of so many different interacting components that I wouldn't really draw any conclusions from the results that get displayed up here. We have two samples in there. One is worse than the other. On that, they actually have slightly different configurations on their lines. The one I was talking about was for the QBlocks device, but there's actually slightly different variant on the other sample. And the control electronics and the way we've implemented it, it might be uniform, but there's some, we can always do more to make these programs faster and maybe behave better. I would say that on terms of quality, the majority of the difference between the two would probably be dominated by the device in this current situation. But that's just my guess. Yeah.
100% sure.
Yeah. I would. Well. Yeah. Yeah.
Okay. Thank you.
Yeah.
Is the software designed to be used by future organizations? Or can you just put a pretty new chip inside which it will find people?
So you're asking, does it do the initial steps? Yeah. I mean, we will be. This is something we're also going to be adding, like how to do set flux values. Find all your resonators in the first place, map those to the right drive or flux lines, set those points, flux crosstalk, etc. But that is something we're actively prioritizing. This is something else as well. Yeah, we are thinking about working on that. And that's something that's very much our next steps. Yeah.
And what happens when experiment fails? Is there some intelligence that something else is executed to finally have a good calibration, or then
that comes down to design of this. In this instance, what happens, because these exit ports don't go to anything, and in the case that you output on something that doesn't actually link to anything, it says this workflow needs your attention, and then it flags it red, and it brings you have that there, so you can have a draw to it essentially, and that's kind of part of the design of the software. In the case where you've identified common problems, it would be about trying to think about, perhaps I don't find my resonance, maybe I need to kick off a larger scan with more density, or identify these types of cases where you should have failure mode sort of handling, and these blocks can help you do that.
My other question is, so you have these nice workflows, and you get a nice characterization. How good is that characterization compared, let's say, to the expert that knows the chip in and out? Have you benchmarked yourself?
That's a really good question, actually. No, we haven't. I mean, we haven't tried to do sort of a comparison against a human test. This is something we could think about later down the line. That's yeah. But I mean, I know typical values that most people tend to get in literature when you expect and other people who have similar types of devices. So trying to see, if I sat down on a computer, would I perform at the same speed? How would I perform? Would I choose similar values? That's an interesting question. But
that also gets to an interesting idea. There was a widely, kind of televised match which IBM sponsored, where the computer beat a human at chess. DeepMind sponsored between Go competition between man and that, and maybe we can sponsor one. You against our system, trying to make a 2-qubit chip,
Not really,
or some expert.
What there are data available for is that the underpinning research at the University of Oxford, which this is now made available to all users, we did actually do the very experiment that you're talking about, and the answer was that the machine, even at that stage, which was some time ago, was very significantly faster than the best humans. And I can actually give you the actual numbers of the data so that you can see them for yourself.
So my answer was not necessarily, okay, yes, your approach will most likely be faster, okay, than a human will be. But the question is, okay, will a human expert, okay, be able to, achieve better fidelity and things like that than what your workflows are able to do?
The other way around. It was that sometimes the humans were unable to tune the thing at all, and the machine was able to find the sweet spot of the tuning where humans failed, in a few cases, not very many, but a few cases.
I mean, it's actually an interesting question about trying to do human versus experiment benchmarking. Because everyone behaves differently as well. But it's an interesting question, and actually I find that area kind of fascinating. So it's something that might be we might be thinking about in the future.
Of course, the other important comparison, once you've done all the ones that you talked about, which are very important, once you've done all those, is then scalability. And scaling humans is very costly compared with scaling computers.
Any other questions?
Thanks for nice workshop. It's pretty good. Actually, I was just wondering about the simulations that you showed as well.
Yeah.
Are you using can you use this data to provide noisy simulations that IBM also have? Of course, it's not working as it should, not that great level, but can you use your data to design something like noisy simulators that can mimic the device at some point?
It's okay. Maybe simulator isn't the correct word. It's more like a sort of emulator in a sense. Like the whole practical purpose of having a simulator in this case is really for test development. So I want to be able to make a simulator that mimics the kind of data I normally see, perhaps using some, even introducing tricks that you might see in certain types of instruments like problems when you might sweep NCO or things like that. Which means actually the simulators are kind of, you could think of it as a compositional selection of models that cover different problems that we are experiencing under individual different cases. So it means that it's not really like this sort of massive simulator that might be great for simulating these cases where we have lots of interdependency. But as we get towards bigger systems, we have to think about things that test that. So we're kind of thinking about the simulators as covering what needs to be tested to guarantee these things work. So the requirements are almost interlinked.
Excellent. Any more quick questions?
Just a quick question.
Quick question. Okay.
Just wanted to, so this flowchart is quite algorithmic, but typically the hardest part of kind of automating this process is when there's weird things like maybe a spurious peaks in your spectroscopy or things which you typically don't see, and that's when human intelligence is needed to kind of intervene in this flow and then change things. So can you comment on whether this would be robust to that, and if yes, if you can comment on how that is done and like.
Yeah, I mean, the real challenge here is trying to make analysis that has seen a lot of different cases and failure modes, and treating almost these ports as symmetric. So a false positive and a false negative are as bad a failures as each other. So I mean, if one of these things flags positive in a case where it shouldn't, that is that is actually quite bad. So we need to get better at designing that, and we're fundamentally doing a lot of testing against positive and negative cases to be able to manage them both. That's, I guess, part of the explanation. But I mean, this means we have to bring smarter tools maybe to the table to get better at this. But it's an ongoing challenge, and I understand that. That's a very big detail. Yeah.
Perfect. And last question.
I'll be quick. So does it currently work only with QBlocks and quantum machine, or can one choose easily his favorite electronics?
So Zurich Instruments so at the moment we have QBlocks and QM. Zurich Instruments is in the pipe. We have a smaller setup from Gen 1, but we are waiting for Gen 2 to be used for...
It's integrated in your instruments.
Yes.
And
So
quickly and one. Can you, so if you were to change, for example, the flux bias, so all the completely random values, does it define the qubits immediately in 3 minutes, or?
I mean, in this case, it depends how much you change it by. I mean, we are inputting, obviously there's some sort of initial estimate of where the qubit frequency is. I know if your qubit frequency jumps off by, I know, gigahertz, then it would be down to one of these failure cases where you do a large scan, try and find where you're back at, and then try and press back and jump back into this workflow. So this version, no. The blocks we got here, yes. Good.
Okay.
Great. Thank you so much. We will go back to the slides quickly to wrap up. If you guys have any questions or comments that you'd like to leave on these pieces of paper, that would be great. So we can use them. It's really valuable to us. Just to wrap up, so we really see that this automation of QPU tune-up brings value to our customers, and this is something that we will continue working on. You see, there's a lot to be done. It scales with number of qubits, so the scalability is built into the architecture of the software. As we heard already, sometimes the hardware is not enabled, and we're not there yet in the development. More electronics will come. If you are interested in integrating something special, come to us and let us know. And of course, adapts to any quantum technology in principle. So we're now with superconducting transmon. Clearly, we will be working on different versions of the superconducting technology, the major ones, and of course the company has been spun out of the spin qubit lab. So this is something that we have extreme deep know-how. So we will develop products in that direction as well. So this is all for us. Thank you so much for coming. This is our team, and here's our email, contact@QuantrolOx.com. Write to us, and let's start working together. If you have a chip you'd like to try out with the electronics at the moment, or you'd like to install it and start using it, just let us know. Thank you so much.